are the general ideas. So let's play with that. The idea is that moving conductor through magnetic fields can create potential sources. And if I have closed loops and I look at the flux flowing through them, I can use Lenz's law to understand the direction of induced current flowing around in those kind of circuits. So what about this one? I have a metal bar that's moving through a magnetic field. The magnetic field points downwards and this conductor is also moving downwards. How are the charges going to separate in this conductor? Can you identify which charge separation is indicative of what would happen in this case? I'm going to give you guys about 15 more seconds. All right, let me go ahead and end the poll. Pretty mixed across the board here. Okay, we didn't like B, but pretty uniform for all the other answers. Well, let's see. Let's think about the positive charges that are in this conductor. The force that acts on them from this magnetic field is QV cross B. Let's use my right-hand rule. Well, this is QVB sine theta, right? The magnitude of that force. What is theta in this case? Remember, theta is the angle between QV and B. In this case, the angle theta is equal to 0. So that means FB in this example is 0. There's no force that's going to be acting on these charged particles, so there's no force that's going to push them to one side of the conductor, so there's no charge separation here. Right? Remember, we saw that last week, that if the charged particle is moving in the direction of the field, it doesn't experience a force. It's only if there's a perpendicular component. Okay, so be careful about that. I can move a conductor through a magnetic field without generating potential. I have to be moving it in the direction of the magnetic field. Okay, what about if I do this? Now I've rotated that magnetic field so it's pointing out at us. How did the charges separate then in this example? Think about the forces that are being exerted on the charged carriers inside of the conductor. What direction does the force that's created push those positive charges? Okay, I'm going to go ahead and close the poll in 2 seconds. Poll is closed. Okay, most popular choice was B, closely followed by A here. Let's see, we can use our right-hand rule. Remember last week, cross product, we align our index finger with the first vector, V points downwards, B points back at me out of the board. So that means my thumb tells me about the force. The force on these positive charged particles is going to point. It's going to point to the left. That means the charged particles are going to be driven to the left and gather on the left side of the conductor, leaving the other side negatively charged. Okay, so let's think about Lenz's law now. We have this piece of conductor that's moving. Well, we can think about this in terms of the voltage source here. So we have this piece of conductor. Now we see that there's a current that's generated around this loop. Okay. What direction does that mean the magnetic field has to be pointing in this example? So think about this in two ways. Think about whether or not this side of the loop has to be positive or negative, right? Which one is it? Is it positive or negative based on what you know about the current there? And then once you know that, can you determine what the direction of the magnetic field? So how is the magnetic field oriented in this case? All right, I'm going to end the poll. Most popular answer was C, into the screen. So I see the current flowing in this direction, right? We know that the current around a current carrying loop wants to flow from the positive side of our voltage source back to our negative side. So that top side of that conductor better be negative. That means that the force FB on a positive charge better be pointing up. It's pushing those charged particles up. Okay. I see the velocity is in this direction. I know Q is positive, so QV points in this direction. And so I can use my right-hand rule, right? My index finger is going to point in the direction of QV. My thumb is the resulting force, and so that gives me that my middle finger has to be pointing into the page or into the screen in this example. So I know B has to be pointing into the screen. So now let's think about the flux. Okay, so we understand this idea about moving conductors create electric potential. But now we also have this idea that if I have changing flux through some loop, it generates an induced current. So let's just try a couple quick ones about the flux. Remember, my magnetic flux was defined as A dot B, or A B cosine theta. So here's two setups. I have magnetic field in A and B, both pointing out of the page at me. The loop, right, there's some length. Each of these has length L. This one on the bottom has length 2L for each side. And the magnetic field is twice as strong on this upper one. So if this is B1, then this guy B2 is equal to half of B1. Which one has more magnetic flux through it? Which of those two loops has more magnetic flux through it? Okay. Let's go ahead and end the poll. Most popular one was B, loop B. Okay, well, let's see here. The angle theta for both of them, right? The area vector and the B field are aligned with one another. So we can take this to be 0. Okay, so cosine of 0 just gives me 1. So this is like A times B. So magnetic flux 1 for that upper one, or magnetic flux A, is going to be L squared, right? The area of the loop times magnetic field 1. What's magnetic flux B? Or let's call that magnetic flux A, I guess. Magnetic flux B is going to be the area. Well, that's going to be 2L times 2L. That's going to give me 4L squared. And then that's going to be BA over 2, the strength of the magnetic field. You can see a factor of 2 cancels out here, and I'm left with something that's like 2L squared times BA. So the flux through B is twice as large as the flux through A. All right, so now let's think about Lenz's law. We want to start thinking about the induced current. And what we know is that we're going to be looking at the change in the magnetic field. So if I have a change, right, a change in the flux, change in the magnetic flux implies that there's an induced current. Excuse me. What direction does that current want to flow? It implies that the induced field, right, opposes the change in the flux. So what about this example? I have a uniform magnetic field everywhere here. I'm pulling this loop through this field. Just imagine that the magnetic field extends off as far, like off the edges of the page as far as you can see, and it's uniform everywhere. Will there be an induced, is the magnetic flux changing through this loop? Remember, it's A, B, cosine theta. Are any of those 3 variables changing in this problem? All right, let's go ahead and end the poll. Most of you are selecting that no, there's no change in the flux, right? The area is fixed. The size of the loop isn't changing. The strength of the magnetic field isn't changing, and I'm not rotating the field, so there's no change in the orientation between the vectors. So that implies that none of my 3 variables are changing, so there's no change in the flux through that loop. What about this one? Same idea. The loop is moving, but now instead of being pulled to the right, it's rotating. Is there a change in the flux in this case? Is there a change in the flux? All right, I'm going to go ahead and end the poll. Show the results. Right, there is a change in the flux. Okay, why? Because what's changing? Theta is changing in this example. Whoa. The angle, right? That A vector originally points out at us, and as it rotates around, the B field stay fixed, and that A vector is changing, and the angle between them is altering. So I have more flux, more and less flux depending on the orientation. So now let's try to put it all together with trying to understand the directions of the induced currents using Lenz's law. So in this example, I have a permanent magnet, and there's a magnetic field that points in this direction. What's going to happen to the current in that wire as that magnet approaches that loop? Is there going to be an induced current that flows clockwise, counterclockwise, or no induced current? What do you guys think? All right, let me go ahead and end the poll. Split results between clockwise and counterclockwise induced current. So what's the chain of events? We need to check to see if there's a change in the flux. A change in the flux would imply there's a change to one of the variables inside of the flux. Well, A is the flux window. That's not changing. That's fixed. The orientation of that loop to the field is not changing. So cosine theta is fixed. But the B field is changing, right? The strength of the magnetic field is higher close to the magnet, right? The field lines are all concentrated at that north side. So I get a stronger magnetic field as I bring that magnet closer to the loop. So the B field is changing. So there's a change in the magnetic field that's creating a change in the flux. The initial B field is pointing upwards. If I look a little bit later, I can find that there's a final B field that's still pointing upwards, but that is going to be stronger because that magnet is moving closer to the loop. So delta B, right? B final minus B initial is going to point upwards. Right? If I take the difference between those two vectors, I get a delta B vector that's going to point upwards. It's increasing that upwards pointing magnetic field vector as I point through here. The induced field from the current, Lenz's law tells us that the induced field has to oppose the change in the flux. The change in the flux points in the same direction as the change in the field in this direction. So the change in the flux has this upward sense to it. So that means I need the induced field to point downwards from the currents. Where does that induced field come from? It comes from the circulating current that gets created by the changing magnetic field. I can use my right-hand rule. If I want the current to generate a downwards pointing field, I need, right, my thumb is the field, my fingers circulate around the loop in the direction of the current. I need the current to be circulating in the clockwise sense. Okay, so that's the chain we have to follow for Lenz's law. Find the change in the flux. Find the orientation of that change in the flux. The induced field has to point in the opposite direction, and the induced currents have to be generating that induced field. What about this one? I have my bar magnet now laid down on its side, and I bring it close to the loop. What happens to the current in that loop in this case? Okay, I'm going to give you 5 more seconds. Okay, let's go ahead and end the poll. Most popular answer is that there's no induced current. That's correct. Why is that correct? Well, what do the field lines look like? The fields come out of the north side and come back and return to the south side. Oops, that was drawn terribly. Let me try again. Okay. Something like this. So look, it doesn't matter how close I bring the magnet here, that I can always find that the field lines are either perpendicular to that plane, so they wouldn't generate a flux. Over here, the magnetic field is, some of it is, there's a component of it that points downwards through the loop. But over here, I'm going to be able to find a counterpart that has a counteracting piece of magnetic field that's going to point upwards from the loop. So if I divide this loop in half, I'll find that on this half of the loop, I'll have a flux of the magnetic field that's pointing upwards through the loop. And on this half, I'll have that the magnetic field is pointing downwards, and in just the sort of symmetric way that's going to counteract the flux on the right-hand side. So the flux through this thing is going to equal to 0, no matter how close that magnet gets to the loop. If the flux is equal to 0, at all times, then there's no change in flux. And that implies, right, the change in flux is equal to 0, and that implies that the induced current is equal to 0. So there's no induced current here. Okay. So let's look at 3 more examples, see if we can get through three separate problems here as we go along here. So I have this current carrying loop that you see here, and I have a magnetic field that points into the board. And what I want to know is if the current is going to circulate clockwise, we're going to use A to indicate clockwise, B to indicate counterclockwise, and C if there's no current flowing. What happens to the current in this loop if the magnetic field strength is increasing? The magnetic field strength is increasing. What happens to the current? Hi guys, can people hear me now? My Zoom crashed out on me there.
Yeah, you're back.
Okay, thanks. Okay, let me go ahead and end the poll. Okay, so most of you selected A, that this thing would be circulating in the clockwise sense. Okay, so we need to find the direction of the change in the flux. Well, it says the field is becoming stronger as I move, right? As I move into the right? It's the inwards pointing field is becoming stronger. So that means that my initial field points into the board, and if I wait a little bit longer, I get an even stronger field pointing into the board. So that means my change in my magnetic flux, right, is into the board or into the page. My magnetic field is more and more strength pointing into the page. So that means my induced field should point in the opposite direction. So I want my induced field from the current to point out of the page back at me. I can use my right-hand rule then to get that my I can use my right-hand rule to get then create a field pointing out at me that I need current circulating around in the counterclockwise sense. Okay, so the answer here is B. Okay. What if the field strength is constant? What happens if the field strength is constant? give you guys about 5 more seconds on this one. If the field strength is constant, then I don't get a change in the magnetic field. If there's no change in the magnetic field, there's no change in the flux, and so I don't get an induced current. What about C, if the field is decreasing? Well, if the field is decreasing, I'm just going to work this one through with you guys to start without the poll so we can move a little faster since we had a Zoom crash there. If the field is decreasing, then my initial field points into the board. My field a little bit later also points into the board, but it's smaller in size. So that means my change in my field, the change in my field is coming back out at me. The difference between those 2 points out of the board. And that's the same direction as my change in the flux. And that means my induced field has to point in the opposite direction of the change in the flux. So the induced current should be back into the page. To generate a current that points into the page, I point my thumb in the direction that I want that current or that field to go, and my fingers tell me the direction of the current, in this case, clockwise around this loop. Okay. So what about this example? Now, instead of just having a field, we're going to look at the apparatus that's generating a field. So there's a closed loop that we're going to be thinking about the current flowing around in that bolded loop there. And what we're going to do is we have a battery connected to a loop of wire and a switch above that. Okay. We know that as current starts flowing around that upper loop, if I were to close that switch, it's going to generate a magnetic field, right? The circulating current generates a magnetic field that points through that loop. We're going to think about what kind of current that induces in the lower loop. Okay. So again, we're going to think about, does the lower loop of the wire have a clockwise current A, counterclockwise current B, or no current C? So before I close the switch, right, the apparatus is just sitting there as it's indicated on this page. What's the induced current in that lower loop? Okay, I'm going to end the poll. Most of you said that there's no current in that lower loop. Absolutely. If I don't have that switch closed, there's no current in that upper loop. There's no magnetic fields anywhere, so there's no magnetic field for as long as I wait, as long as that switch is open. So there's no change in flux through that lower loop, and there's no induced current. Now what I'm going to do is I'm going to close this switch. And that means that I'm going to have current that's going to start flowing from the positive side of my voltage source back to the negative side. Okay. How is the current? Is there going to be an induced current in that lower loop the moment after I close the switch? So I have a meter and I'm watching for current circulating around in that lower loop. The instant I close that switch, what direction is the current going to flow around in that lower loop, if at all? All right, give you guys 5 more seconds. I'm going to go ahead and end the poll. Okay, so pretty mixed results here. Let's think about this. Well, is there a change in the flux? The initial current, the initial magnetic field was 0 when the switch was open. Once current starts flowing around in this thing, now I get this upwards, right? I can use my right-hand rule to find that I get an upwards pointing field. So that means the change in the flux, and right, that same field is going to penetrate through that lower window there. So I'm going to have a change in the magnetic field that points upwards, right? It went from 0 to pointing up, so there's a change in magnetic field after that switch is closed that points upwards. That's also going to indicate that there's a change in flux. That means the induced field has to point downwards. It has to oppose that change in the magnetic field. To create that downwards pointing magnetic field, I'm going to have the current circulate around in this thing in the counterclockwise direction, or sorry, in the clockwise direction, the opposite direction of the current in the loop. What about B, after the switch is closed for a long time? Well, if I wait a long time, there's just a steady current that's going to be flowing through that upper loop. It's going to be generating a magnetic field that's fixed B. And so the initial magnetic field would be pointing up. And if I wait a little bit of time longer, that magnetic field is going to be the same. So if I wait a really long time, there's just going to be a steady magnetic field. And so I won't get any change in flux and I won't drive a current around in that lower loop. So what happens is I close the switch, I see a spike of current in that lower loop circulating around in the clockwise sense. And then as that B field in the upper loop stabilizes, that magnetic field will die away. And if I wait a long time, it'll just go back down to 0. What happens after I open the switch? So now the magnetic field is stable and I'm gonna open the switch. What happens to the current in the lower field if I reopen the switch after the magnetic field has been running around for a while? I'll give you guys 2 more seconds to think about it because we're running short on time. All right, let's go ahead and end the poll. Most popular answer was that it's going to go counterclockwise. Well, let's think about this. In this case, the initial B field was going to point up. Then after I open the switch, the B field is going to go to 0. So the delta B, the change in the B field, is going to point downwards. It went from pointing up to being 0. So that means if I take B final minus B initial, I'm going to get a downwards magnetic field, right? That's the same direction that the change in the flux has to point. That means my induced field has to point upwards, the opposite direction of the change in the flux. To get an induced field in that direction, I need current that's going to circulate counterclockwise around here. Okay, we're going to go ahead and stop there for today. We're out of time. We'll pick up with this idea tomorrow, and we're going to also introduce Faraday's law, where we're going to try to get a little bit more quantitative and understand how much current and the magnitude of the potential that's generated from these changes of fluxes through these loops. All right, I can stick around to answer any questions you might have. Otherwise, have a great day. Thanks for sticking with me through the Zoom dropout, and everybody have a good one. I'll see you tomorrow. Bye now.